One-dimensional gravitational motion. It takes 2.5 seconds for a small ball with a mass of 0.14 kilograms that's released from rest from a tall building to reach the ground. Calculate the height from which the ball is released, assuming that air resistance is negligible. Alright, so a couple things about this problem. First of all, there's two equations that we could be dealing with. We could be dealing with the displacement equation, and we can be dealing with the acceleration equation, right? If we look at those equations, there's 5 different measurements that are part of these equations. We have displacement, initial velocity, time, acceleration, and then I have time again. I have acceleration again, final velocity, initial velocity, which we already said, and time. So there's 5 things, 5 measurements that are part of these two equations. So when we're looking at this, there's a few things we want to do. We want to draw a diagram, and we want to list of those 5 things, which things do we know. So looking at this situation then, first we will draw the diagram, kind of nice and simple on this one. Here is my building. Here is my ball. And I know the ball is going to go down. And I know the time. It is going to take 2.5 seconds to go down. My writing's not so great on this. Alright, so now when I look at this, there's 4 other things that I could know, and that's what I need to start thinking about. They gave me the 2.5 seconds. They also gave me a mass, but if I look at the 5 things that are important for solving this problem, mass isn't on there. So yeah, I could put it down, but I could also see that it's not really important to the information I'm looking for. So there has to be more that we need to know. So when I look at this, I say, okay, it is released from rest. So that means I know my initial velocity. It's 0. It starts to fall after. And it's falling through the air, so it's in free fall, so I know my acceleration. I'm going to stop trying to write these in and just kind of put them down. So I know, let's erase, I know these things. I know my initial velocity because it started from rest. I know my time because it was given. I know my acceleration because it's a free fall problem. So these are all the things that I do know. These are the 2 things that I don't know. I don't know my final velocity and I don't know my displacement. But I'm looking for how tall the building is. Well, that's a measure of length, and displacement's a measure of length. So I'm going to be using my displacement equation for this problem. Now, just to go back and say it, I do write it slightly different. I usually list displacement as an x, and I realize in the equation that I showed, there we go, displacement's a d, but it's still this value right here that I'm looking for, right? So we could take that out if we wanted to, and we could just put an x into that equation, right? So initial velocity times time plus 1/2 acceleration times time squared. When I look at this, I know my initial velocity. My initial velocity was 0. So I can take this and I can take all of this out. What's 0 times time? Well, 0 times time is 0. So that's gone. So now displacement equals 1/2 acceleration times time squared. Let me just get to a blank sheet. Here we go. So I'm going to have displacement equals 1/2 negative 9.8 times time squared, and my time is going to be 2.5 seconds. So I'm going to rewrite this again. But there's my values, 2.5 seconds, and I've got to square that. So now I'm going to do this, but I am going to do this with unit analysis, right? But I know what I have to put in. I know what disappears from this equation. I have everything I need. So I just want to write this up again, and I want to look at the units. I'm looking for a displacement. So displacement's measured in meters, or I'm looking for the height of the building, and still that's measured in meters, right? So I'm going to have 1/2 times negative 9.8, and the units for that are units for acceleration, so that is going to be meters per second squared There we go. And I'm timesing it by time squared. So I'm timesing it by 2.5 twice. 2.5 seconds. And then 2.5 seconds. There we go. Now when I look at this, I can excuse me, I can cancel out the seconds. I have 1 second here. That gets rid of one of the ones on the bottom. I have another second up top. That gets rid of another one on the bottom. So my units that I'm left with are meters, which is good because I'm looking for a length, or displacement is measured in meters. So I know I'm plugging in my numbers correctly because the units are telling me that I'm plugged it in correctly. I do this. It's going to be 0.5 times 9.8 times 2.5 times 2.5 again. 0.5 times 9.8 times 2.5 times 2.5. I get a negative 30.65. A negative 30.65 meters. Now, I've got to answer the question correctly, but I did the math right? And I get this value. And I know it's right because my units are right. And I also know it's right because it's negative, and that makes sense. The ball will be 30.65 meters below me, and that's what the negative's telling me. It's telling me it's going down, so it's going to be beneath me at this point, right? But if I'm going to calculate the height, well, the height is how tall the building is. The building isn't in a hole, right? It is going up. So my final answer has got to be positive, right? I need to understand what the negative meant. But I also, once I know what it meant, I can get rid of it because I am looking for not how far did the ball fall, but how tall is the building. Well, the building had to be 30.65 meters tall so that the ball can fall from that height. And there's my problem. Now, the second part asked, what is... For the second part, if that ball had been released from the same height, but this time above the surface of the moon, how long would it have taken the ball to hit the ground? So now we know some information we didn't know before. Now we know a height, so 30.65 meters. Again, I'm making it negative this time because that's what the ball is going to do. It's going to go down 30.65. I have an acceleration, which just means I have to Google the acceleration on the moon. And I still have an initial velocity. So this is my given information at this point. I am looking for a time. So again, going back to the two equations I could be using. I have a displacement. I have an initial velocity. I have an acceleration. The only thing looking at this equation that I don't have is time. So that's the equation that I'm going to be using. I set this up. I know this. Initial velocity is 0, so initial velocity times time is going to work out to be 0. So I could basically get rid of all of that, and it's going to be plus 1/2. And I know gravitational acceleration on the moon. I'm just going to put g for now, and then time. So if I rewrite this equation, it's not so bad because this part's gone. It's going to be 2 times the displacement, negative 36.5, divided by the gravitational acceleration on the moon. That's going to equal t squared. So I need to solve for t, so I got to take the square root of both sides, which is going to allow me to get rid of the squared. And there is the equation I'm going to use. So it's going to be 2 times negative 30.65 divided by negative 1.67. Right? If I set that up, then it's going to be 1/2. Let me clear this. It is going to be 2 times negative 30.65 meters divided by negative 1.67 meters per second squared. I could already see meters are going to cancel out. I'm left with seconds squared, but it's the square root of this, so my answer is going to be seconds.